Welcome to our photochemical smog presentation.
Let's start out with the precursors to photochemical smog.
One precursor is NO2, which is primarily released from the combustion of fossil fuels, such as from car exhaust.
Next up, we have VOCs, also known as volatile organic compounds, that bind with NO to form photochemical oxidants. VOCs come from gasoline, formaldehyde, cleaning fluids, oil-based paints, or coniferous trees.
And lastly, we have O3, or ozone, which forms when NO2 is broken by sunlight and the free O binds to O2.
Now let's look at daytime formation of the tropospheric ozone.
The sunlight breaks NO2 into NO and O. The O then bonds with O2 from the atmosphere to form O3. The formation of ozone tends to peak in the afternoon when sunlight is most direct and the NO2 emissions from the morning traffic are highest.
Moving on to nighttime destruction of ozone.
During the nighttime, the O3 reacts with NO to form NO2 and O2 again. The O3 levels drop overnight.
How does photochemical smog form? The process starts with the same. Sunlight breaks down the NO2 into NO and O. Then the O bonds with O2 to form O3. VOCs and the NO from NO2 bond to form photochemical oxidants. Due to the lack of NO to react with, the O3 builds up overnight. The O3 and photochemical oxidants then combine to form photochemical smog.
What factors increase photochemical smog formation? One such factor includes increased VOC emissions, which can come from gas stations, laundromats, or petrochemical and plastic factories. These are especially prevalent in urban areas.
Another factor includes increased vehicle traffic. Increased vehicles can lead to an increase in NO2 emissions, thus O3 formation, especially in urban areas which tend to have more traffic.
The next factor we have is increased sunlight. More sunlight, especially in the afternoon and summertime when sunlight is more direct, can lead to an increase in ozone formation.
Atmospheric and urban factors can include warmer temperatures. Warmer temperatures can speed up the evaporation of VOCs and can also make the reaction leading to O3 formation faster. In urban areas, the presence of blacktop with lower albedo can lead to more smog.
One last factor that can be seen, especially in urban areas, is an increase in electricity demand. Due to a higher demand, more NOx is emitted from nearby power plants.
Let's look at the impacts of smog.
Starting with environmental impacts, photochemical smog can reduce sunlight, limiting photosynthesis. It can also damage plant stomata and irritate animal respiratory tracts.
In the case of human impacts, photochemical smog can act as a respiratory irritant, worsening asthma, bronchitis, COPD, and irritating the eyes.
Lastly, we have the economic impacts, including increased healthcare costs to treat asthma, bronchitis, and COPD. There can also be productivity loss due to sick workers missing work or dying. Due to less sunlight reaching the crops and damage to plant stomata, there are also decreased agricultural yields.
To end off, we have methods to reduce the amount of photochemical smog in the atmosphere.
We can increase electricity from renewable sources that do not emit NO, including solar, hydro, and wind power, to name a few. Natural gas power plants also release a lot less NOx than coal.
Second method to reduce photochemical smog includes decreasing the number of vehicles on the road, which in turn decreases NO2 emissions. Carpooling, public transport, biking, walking, and working from home are potential solutions. Fewer vehicles on the road requires less gas, thus fewer VOCs.
Thank you!